galaxies in the red and lenticular galaxy in blue. And if you look at the fraction of these three classes of galaxy as a function of density, which is plotted in the x-axis, then in the low density environment, most of the galaxies are going to be spiral structures. Whereas in high density environment, most of the galaxies, they have either these spheroidal elliptical types or lenticular types. And we think that interact because in dense environment, you have a lot of galaxies around each other, and this galaxy interaction, they kind of destroy the nice spiral disk structure and transforms them into the spheroidal type systems. Another thing that we have learned over the past 20 years or so is that galaxies in really dense environment, they are hardly forming any stars. So the figure here shows the average star formation rate as a function of distance from the center of a major cluster. So if you think the right side of this plot is a low density environment, like we call it field, it's just average density environment. And the left side is the cores of the cluster. And if you look at the mean star formation rate, then in the field environment, then in the center of the clusters, the galaxies are hardly forming any stars as compared to the field environment. The star formation rate declines gradually as you go inside the environment. So during my PhD, the question that I was interested in was, we know that the clusters or the environment affects the morphology and the star formation rate. Does the environment affect the rate at which galaxies are producing metals? By metals, I mean anything which is not hydrogen and helium. That's the definition of metals in astronomy. Since most of these, and there is a reason for it, because most of these elements, they are produced within the stars and through stellar evolution and the processes within stellar evolution. So you go from gas cloud, you make stars, and then you produce metals. And we know that environment, I've shown you in the previous two slides, that environment suppresses star formation rate. In dense environments, galaxies are hardly forming any stars. So does environment also affect the rate at which galaxies are producing metals? Galaxies are building up their chemical content. Okay, to answer this question, we usually look at mass metallicity relation, because there is a very strong correlation in the metal content of a galaxy and the stellar mass. You can see on this plot that massive galaxies, they have much higher chemical content than the low mass galaxies. It's about 10 orders difference. 10 orders, 1 order difference, sorry. Right, so if we want to understand if and how environment affect metallicity of a galaxy, we usually look at the difference in this mass metallicity relation depending on where the galaxies live, depending if the galaxies live in a cluster or in an average density environment. And this has been done for the past 10 years by a lot of people in a lot of different ways, myself included. And this figure shows the mass metallicity relation, or the metal content of a galaxy as a function of stellar mass in two different environments, cluster and field. Field is average density, low density environment. And you can see that there is hardly any difference. It looks like between the two environments, the amount of metal content in a galaxy is pretty much the same. And this similar conclusion has been reached by a lot of other people with using various techniques. But one thing that I'll point out, and most of this work is done at redshift of 0.1, redshift of local universe. The redshifts can differ a little bit depending on which study you are looking at, but it's very nearby universe. In nearby universe, most galaxies in a cluster environment, they are hardly forming any stars. And if you want to measure the metal content of a galaxy observationally, they need to be forming stars. Otherwise, you cannot measure this gas, the amount of metals in the gas of the galaxy. So we are really limited in observations how we can measure it, because most of the galaxies whose metal content could be affected because of the environment, they won't be directly observable in observations. So what do we do? And what I did was, there's the number of things you can do, but what I did was I tried to look at this effect in simulations, in particular cosmological simulation. And this is an animation showing illustrious simulation and evolution of the entire universe. And it kind of shows that how different galaxies and structures sort of evolve in this simulation. And right now what's happening is number of supernovae are going on, and the red color is for the metals, all the metals that are getting blown out by this supernova explosion. Slowly with time, these supernova, the gas is going to cool down and settle down, come back into the galaxy, and is going to enrich the galaxy, make next generation of the galaxy, which already will have this metal content. Okay, so fantastic. What's the advantage with cosmological simulation? In cosmological simulations, they are simulating these galaxies and they have this large scale environment around the galaxy. So we can ask this question, does the metal content of the galaxy differs depending on where the galaxies live in this simulation? And to do this, what I did was I looked at all the galaxies which were in clusters in the local universe. We tracked them back in time. It's a simulation, so we have the full evolutionary history of the galaxy. And at every time step, we identify if the galaxy was part of the cluster at this time stamp or not. And so we separate the galaxy into two classes. One is galaxies that are yet to fall into the clusters, and the red is galaxies which are already part of the cluster. And then you can see the full evolutionary history of you can build up the full evolutionary history of the cluster. This is done to figure out if galaxies fall into the cluster, do they already have higher metal content, how they are falling into the cluster, and after falling into the cluster, when do they build up their metal content? So there's a lot of advantage of doing it this way. Okay, great. So what do we learn? This is again mass metal history relation in illustrious TNG simulation, plotted at redshift of 2, which is about 10 gigayears from the present universe. And I'm plotting galaxies in two different densities. On the galaxies in the high density environment, these galaxies are already part of the cluster at redshift of 2, and then comparing their mass metal history relation with galaxies in the low density universe. At redshift of 2, there does not look like there's any difference in the metal content of galaxies in these two environments. If we go on to redshift of 1.5, we do start to see some differences appear. And as we move on to lower and lower redshift, we found that most of the galaxies which were part of the clusters, they had consistently 20% higher chemical abundances across different stellar masses. So beyond redshift of 1, most galaxies in the cluster environment, they have higher chemical content by about 20%. The number can be, it depends on the chemical evolution model, but sure, there is an effect of environment. Another interesting thing that we found was, since we were tracking when did the galaxy become part of the cluster, so we have this population of galaxies which are yet to fall into the cluster, and we were tracking their chemical abundance as well. At higher redshifts, their chemical abundances look very much similar to the blue triangles, which are the galaxies which live in low density environment. But at lower redshifts, for example, redshift 0.5 and below, the chemical content in these galaxies which are yet to become part of the cluster was also higher than the typical field galaxy. It was higher by about 10% only, but it was higher. And we think that because these galaxies which are yet to fall into the cluster, they don't come as individual galaxies. They are not isolated before they fall into the cluster. They are part of a smaller group. They come in a bunch of 2, 3, 4, or 10s of galaxies. And because they are part of these smaller groups, the interactions between these smaller groups is also boosting the chemical content of these galaxies, which are yet to become part of a larger structure. So, which is quite cool. And another thing that we figured out through this work was, why was the metal content of these galaxies in higher density environment higher? Because it is higher by 10% or 20%, depending on which sample you're looking at, but why is it higher? And we figured out that because in simulation, you can track where the galaxies are, where the gas in the galaxy is coming from. So you can figure this question, ask this question. So what we found was, as the galaxy, they fall into the cluster environment, they go through this intra-cluster medium. And intra-cluster medium has the pockets of gas which is already enriched in the metals. Because intra-cluster gas is full of gas which has been coming out from all the galaxies that are part of the cluster already. So it already had some chemical content. It's not just neutral hydrogen and helium, it has some other elements as well. And as galaxies go through this intracluster medium, some pockets of this metal-rich gas, they and end up in the galaxy that is currently falling in. So instead of just building your chemical content through stellar evolution, through the supernova going off into the galaxy, you build up your chemical content by accretion of this metal-rich gas as well. And that is why we think that galaxies in a dense environment, they have higher chemical content. It's this accretion of metal-rich gas from the surrounding medium that's boosting the overall chemical content of galaxy. So it's quite cool, which is an interesting conclusion. And there has been a bunch of observational work as well, which kind of reached the same hypothesis in the past 2 years or so, that galaxies that seem to have in dense environment, they seem to have higher chemical content. And it's probably due to the secretion of metal-rich gas, which is nice. And over the next sorry, I lost my chain of thought. But that's all right. Oh yeah, I was going to say, over the next couple of years, we have been investigating this further with Anisha Hershen, I am co-supervising at UNSW Sydney, and she'll be talking more about how galaxies affect their environment tomorrow. I think tomorrow she's giving the talk. But my work since PhD has focused mostly on the high redshift universe and looking at how galaxies evolved in the high redshift universe. So I'll move on to the second half of my talk, which is this Epoch of Reionization type work. And just to reiterate, Epoch of Reionization, essentially, this is this phase where you can see these bubbles surrounding the galaxy. The bubbles are essentially the bubbles of neutral hydrogen gas that are created because galaxies, they are just enveloped by this neutral hydrogen, and the photons in the galaxies, they are clearing out some of that neutral hydrogen, but there's still a lot of neutral hydrogen to be cleared out. And this is called Epoch of Reionization. There's been a lot of work that's happening in the Epoch of Reionization, especially with the launch of JWST, and we are trying to look for what were the first galaxies, what were their key properties, how are this epoch really evolved. And there are two key properties of galaxies that are really important to understanding how this epoch really evolved. One is the number of ionizing radiations the galaxies are producing. Because ionizing radiations essentially are the radiations that can ionize neutral hydrogen. And second property is escape fraction, because galaxies, they usually have a lot of hydrogen within themselves. So most of the ionizing radiations that the galaxies produces, they cannot ionize the intergalactic medium or the medium surrounding galaxy. So only radiations that can escape the galaxy itself, that are going to be responsible for this reionization of the universe. Over the next 20 years now, because JWST has been launched and deployed, and it's probably going to last for the 20 years. We'll know a lot about the number of ionizing radiations these galaxies are producing at redshift 9 or 10 or even higher, maybe, we'll see. But since during the Epoch of Reionization, there's a lot of neutral hydrogen still surrounding the galaxies itself. We will never be able to measure how many of those ionizing radiation can escape the galaxy and go on to ionize the intergalactic medium, because all the neutral hydrogen that is in between us and the galaxies is just going to absorb those ionizing radiations. So what do we do? What my solution has been, try to find galaxies that kind of resemble the properties of the galaxies at a higher redshift, for example, redshift 6, 9 or so, the time when we think the Epoch of Reionization was ongoing. Study their detailed properties and then put them back into our models of reionization and try to match those models with the observations. And because if the galaxies are in this ionized universe, we can directly get their escape fraction, which is one of the key parameters, as I said, to understand reionization. So to do this, we are how do we select those similar galaxies? There's one thing that we know of galaxies at Epoch of Reionization or redshift greater than 6 is they have really bright emission line. This is a spectral energy distribution of a galaxy. A galaxy, there are two main components in a galaxy. One is stars and the other is gas that is emitting light. The continuum here, which is this solid black line, you can see, is the most of the emission in this continuum is coming from stars. But all the spikes that you are seeing, that's coming from the gas. Most of these spikes are coming from emission coming from the gas. And the gas which is emitting light, also emitting light, that can be as bright as the stellar component. Basically, the gas, the luminosity, overall luminosity that's coming out in the gas, from the gas, that is equivalent to the star's stellar luminosity. So, which is quite unusual in the present day universe. Most of the galaxy, most of the light that is coming out is coming from the stars. The gas contribute very little to the overall luminosity of the galaxy. But that was not true at redshift 6 and higher. So we can try to identify similar type of system. They are going to be rare, but they are out there. There are some extreme systems that have similar properties. They have their stellar background or stellar continuum is as bright as their emission coming from the gas component. So we try to identify similar system and try to go after them with spectroscopy. So for this, I'm doing this survey, which is called Mosul survey, multi-object spectroscopic emission line survey. And in this survey, we are particularly targeting redshift 3 to 4 galaxy. Why redshift 3 to 4? Because this is a very special redshift regime where we can target the full suite of, so for example, the Lyman continuum regime, which is quite important for understanding reionization, for example, the escape fraction. We can only access that Lyman continuum regime from ground-based spectroscopy at redshift 3.6 and above. And we can 3.4 and above. And we can, and at this redshift, we can access the optical emission lines, which are in near infrared as well, simultaneously. So we get this very nice range of Lyman continuum to optical rest optical signatures from ground-based spectroscopy. So it's quite good. That's why we chose this redshift. So this is our sample. The golden stars and the pink squares is our sample, Mosul sample. And on this plot, I'm showing the strength of emission lines as a function of stellar mass. The red diamond is a bunch of galaxies, median strength of emission line and stellar mass of galaxies at redshift of 8. And you can see that a large fraction of our galaxies, they have similar-ish emission line strengths and stellar mass to redshift 8 type galaxy. And compared to typical redshift 3 galaxy, which are these green diamonds, it's significantly lower stellar mass and higher emission line strengths. So we have somewhat similar sample to redshifts greater than 6 galaxy, which is Epoch of Realization. Right, good. We have the data. What do we do with this data now? And we have really fantastic spectroscopy from both MOSFIRE spectrograph and KMOS spectrograph. MOSFIRE is on Keck telescope in Hawaii and KMOS is on BLT, very large telescope in Chile. Right, so what do we do? The question that I was interested in with this really great spectroscopic data is, do these galaxies, do we see any signs of really large scale galactic scale outflows in this spectrum? Why particularly outflows? Because outflows, they are really important in galaxy evolution. They kind of regulate star formation. The galactic scale outflows, they push out all the gas and are responsible for shutting down star formation. Otherwise, just star formation will keep going on. If you have some sort of flow and the gas can cool down efficiently, it will be really hard to shut down star formation without removal of the gas. And second thing, especially in the high redshift universe, galactic scale outflows, they are going to be responsible for enriching the intergalactic medium and circumgalactic medium. Intergalactic medium, we know, is just full of all sorts of metal ions. They have to come from somewhere. They are only going to form in the galaxy. So some process has to push out those metal ions. And usually we think it's this outflow. So that's why I was really interested in figuring out, do we see any evidence of outflows in this really low mass galaxies and really low mass and high star formation galaxy. And typically we assume, since they are low stellar masses at higher redshift, you should have really shallow gravitational potential, and it's the gravity that's going to bring back the gas. Since you have shallow gravitational potential, it should lead to stronger outflows. Simple, right? Okay, let's see what do we find. Usually to identify outflows, we do this multi-component emission fitting. We sort of look at a secondary broad component in the emission line. This is the stacked spectrum for my sample, one of the stacked spectrum. And you can see this really bright peak in the middle, right? That's coming from the main component of the gas. That's the gas that's associated with the galaxies. That's the gas that's moving with the galaxy itself. And you fit a secondary component, which will be the gas that's moving away, or that has a different velocity, or that has a different motion compared to the galaxy's co-rotating gas with the galaxy. You can see that there is a weak secondary component, which is this pink dashed line. Becomes a bit clearer in the residual plot. So the blue residual is when we just fit a single component. Single component means single Gaussian. And there's a clear peak towards the 510 angstrom, which means that there might be another component that we need to add. So there is another component, velocity component in the gas. And so we add another one, and we do find that, okay, sure, the secondary peak goes away, fine. So what does it tell us about the strength of outflows? You can convert these numbers into some sort of strength of outflow, and that's what we did. Now the golden stars is our sample. This is typical outflow strength for redshift 2 or redshift 6 galaxy as a function of star formation strength. If you have higher star formation, technically or typically, we assume that you should have stronger outflows. But our sample, which are these low stellar mass galaxies, which we thought should have really strong outflows, they have, on the contrary, they have really, really weak outflow signature. Their outflow signature is so far off the chart, because if we have to make it fall on the plot, we'll have to increase their outflow strength by about 5 times or so, which is going to be quite difficult. So we don't see any evidence of really strong outflows in these really low stellar mass, high star formation rate galaxy. So what does it mean for my initial assessment? Like, outflows are really important. We don't see them in our sample. Maybe it means for the star formation, I think it means that maybe just the star formation in this galaxy, because our galaxies, they have really high star formation rate. The star formation in this galaxy is probably going to shut down gradually, just because they run out of gas, and the cosmic flows or the inflows of gas from the filamentary structure is not sufficient to sustain the star formation. It's because outflows are not strong enough to push a large amount of metals, large amount of gas in them. And secondly, for the enrichment of the intergalactic medium, since our sample is particularly low mass galaxies, it might be that even at higher redshifts, it's the massive galaxies that were primary contributor of metals in the intergalactic medium, not these low stellar mass galaxy. There are other caveats to this as well, because we are seeing outflows, trying to see outflows at a particular temperature gas. It might be possible that for these galaxies, most of the outflowing gas is at higher temperature, and we can't access that higher temperature gas through the quantities that we are measuring. But that's one of the caveats for this study. But it's interesting to find, and was surprising to see that, okay, there are no outflows in this low mass galaxy, and we were expecting to find like really strong signatures. So just to summarize the work component that I've talked about, there's two main results that I've talked about. One is how galaxies are, or especially the chemical abundances of the galaxies, are affected by environment. Especially from the simulations perspective, they are significantly affected. Galaxies in the dense environment, they have really high chemical abundances. And we thought that the accretion of this enriched gas through the intracluster medium is what's driving the higher chemical abundances of this intense environment. And secondly, I just presented some initial work that we are doing with the Mosul survey, which are looking at this Epoch of Reionization analogs galaxies at redshift of 3. And the first work that we have done is look at the signs of outflows. in them. And we have found that the galactic scale outflows in these really low stellar mass, high star formation rate galaxies is quite weak. But there's a lot of work that needs to be done in the as part of this Epoch of Reionization analogs work. And so stay tuned, maybe more to come. There's a lot more to come. And if you have questions, please free. Oh no, I have few unsolicited advice as well, right? For you guys, since I'm one of the oldest to graduate here. So one thing that I was asked to do was try to answer, is there something that I would have done differently if I go through BSMS course again? What would have been a useful skill for the new students right now who are doing BSMS? I would say the main thing that I felt I was particularly lacking when I started my PhD was writing. I thought during my time as an undergrad that it's getting to the right answer, solving the equation was the most important thing. Just explaining them to people on paper, it's secondary. It doesn't matter that much. I still believe to some extent it doesn't matter, but you have to be able to explain to others what you have done. If you can't do that in a legible manner, then it's a bit pointless if you want to succeed as an academic. So writing is a big component of being an academic. And my experience has been only in academia, so I can't talk about other fields. And in academia, you have to write papers, you have to write grants, you need money to do research, so you need to write grants. If you are an observational astronomer, you'll need to write a telescope proposal. If you are a theorist, then you'll have to write supercomputing time proposals. So there's a lot of writing that is involved. And sooner you develop this writing habit, the better it will be for you. So when you are trying to write your reports as a research, summer reports or whatever, all the master's report or anything, try to do a good job with it. Try to write it as a paper, because that just gets you into habit of this astronomy scientific writing style. And it's like any skill, I would say. I learned it during my PhD in a very hard way, but it can be learned. And I think this is something that could be valuable and would be great if it can be incorporated in somewhat in the course itself, like how to write academically. And yeah, and there's some information about astronomy opportunities in Australia. There's a bunch of universities in Australia, like a lot more on the East Coast, 2 universities on the West Coast, and all of them have really fantastic astronomy course departments and lots of PhD positions. The community is not as big as it's in Europe or in USA, but it's a quite nice and very welcoming community. I've enjoyed my time here. I'm still enjoying my time here in Australia. That's why I never left Australia after moving here in 2013. There's PhD position that comes out throughout the year, but most universities, they advertise their positions between July and December. So yeah, look for these opportunities. Sadly, there is no most of the universities, they do advertise their position on AAS job register, but some don't. So you might have to look at individual university website to find out what those opportunities are. And if you are interested to know more, please get in touch. Yeah, I've written my email address, and hopefully you'll have access to these recordings. That's it. Thank you.
Yeah, thank you very much, Dee, for a very great talk, and also talking about, the advice that you gave to students, and also talking about the opportunities in Australia. So thank you very much for a very wonderful talk. Bagla sir has a hand raised, so maybe you can unmute.
Thank you. So Anshu, first question about your talk. Wouldn't metallicity correlate very strongly with the ages of galaxies?
This is gas phase metallicities that we are talking about,
Right? But even then, yeah.
It does. So if you look at high redshift galaxy and the low redshift galaxies, because high redshift galaxies are usually the younger ones, and the low redshift galaxies are usually, they have gone through multiple cycles of star formation.
Right.
So it does. So high redshift galaxies, they usually have significantly lower metallicity than the low redshift galaxies, which are the older ones. So that's why when we look at metallicity evolution, we usually look at galaxies at similar redshift intervals.
Right.
Yeah. There can still be differences in the ages of individual system, as you, I think that was your question. But on an average, when you are looking at population level, it's going to average out, and the main difference is going to be just the environment.
See, if you look at, since you started with the density morphology relationship, we do know that clusters are going to form in regions which are overdense, much more overdense than a typical region to begin with. Therefore, effectively, the density parameter in that region is higher, and the gravitational collapse of halos is going to be accelerated. It is going to start much earlier. So what essentially I'm asking is that insufficient to explain the metallicity variation? Do you need some extra boost over and above that?
Okay, accelerated evolution. You are saying accelerated evolution in dense environment. Is that enough?
Yeah.
No, it's not enough, because people have looked at the correlation of metallicity with ages, both in simulation and in observation, and in different environments itself, and it does not look to be enough. So you need some sort of, because here the metallicities that we are measuring, that's a oxygen content versus hydrogen.
Mm-hmm.
It's very specific, so you have to account, and it seems to be more complicated than just accelerated evolution. There is not significant correlation with the age. It's just, yes, there is no significant correlation with the age.
Okay. So the other is not about your talk. You came from a no mathematics background.
Yes.
So you should tell others about how that affected your thinking, and what tilted the balance, and how your experience has been, first in the BSMS program, and then of course later in research.
Yeah. Okay. So yes, I didn't have maths in my 11 and 12. I was trying to be a doctor, not the astronomer doctor. So, and our school didn't offer both science and both biology and math, because it was only me who wanted to do both. So they were like, okay, we don't have enough resources to offer that, so you'll have to pick one. So I picked biology, and yeah. So initially when I came to ICER, I was a bit scared about doing maths. To be honest, I didn't encounter much issue with maths. The issue I encountered was with physics, because in physics, you rely a lot on integration and differentiation, right? And I had not done integration and differentiation in year 11 or 12. So I had to take extra classes from Amit sir, who is still teaching at ICER, I think. So he taught me and Arshdeep, I think, those initial sort of crash course on year 11 and 12 maths in the first semester, or essentially basics of it that was needed for doing anything in physics. And just because of it, I did think initially that maybe biology, because I started off with biology in year 11 and 12. Okay, I'll continue with biology in the undergrad as well. So I did take biology in my third year for the first week, but switched after first week to physics, because I was like, no, it's not really working out. Biology is good. I am interested in evolutionary bio. I am still interested in evolutionary biology and genetics and everything, but only in terms of analytics is something that I preferred, rather than more experimentation with lab stuff, I guess. So I switched to physics, and yeah, I don't think it really affected me in terms of moving forward with physics overall in future. Because you can pick, or I don't know, at least I managed to pick it up. It might not be true for all students, but you can pick up some things, and it's not a lot of things that are taught in years 11 and 12 that you can't learn during your undergraduate study. For physics, essentially, I found it was just the integration and differentiation that was really needed, and I needed that crash course in the beginning to do any classical mechanics or anything. Since then, I don't think it has really affected me. So be all right with it. I guess you can learn, even if you come from a biology background.
So approach it positively is your advice.
Yeah, yeah. It's just few things that you need to know, and it's again it's a skill that you as with anything. Maths, the maths of year 11 and 12 is not really the true maths, as the math faculty at ICER will say. It's only in a thing that you just need to practice, and that practice you can do over the 2 years of first 2 years.
Okay, thank you.
I actually had a question, or sort of, could you go back to the illustrious TNG simulation that you showed and explain it once again?
The simulation slide itself.
Yeah.
Give me a second. Okay.
No. I think it was a few slides after this.
Oh, so you're talking about the results.
Yeah, this one, yeah.
Okay, this one. Wait. So what is happening here is, so what we wanted to do was, since it's simulations, you have the full evolutionary history of the galaxy. You know where the galaxies have been in the past and where they are right now. So we pick out all the galaxies that are in cluster right now, and we go back in time. And each time step in the simulation, we figure out which are the galaxies that are already part of the cluster, and that is these red circles. And then and some of those galaxies were not part of the cluster at this redshift, because the cluster is still building. They are part of the cluster at redshift of 0, but at earlier epochs they won't be part of the cluster. So the green crosses, those are the galaxies that have not fallen into the cluster yet. They will do that at redshift of 0, but at redshift of 0.5 or 1 or 1.5, they haven't become part of the clusters. So you can see that when the cluster starts at redshift of 2, most of it is green, because most of the galaxies are not part of the cluster. As you go to lower and lower redshift, slowly the galaxies are accreting and becoming more red, because they are falling into the cluster environment. By redshift of 0, everything is just red. All of the galaxies are part of the cluster. And this is just a simple animation of showing how a cluster essentially builds. And the circle here, the dashed line, is the line that separates, it's a projected space right now, but the galaxies, they are in a 3-dimensional space. So you can see some green crosses come overlapping with the red stuff, but that's because of the projection effect. I'm plotting, it's a 3D position in a 2D space.
Okay. Thank you very much. Yeah.
No worries.
So in this simulation itself, you have marked few of the galaxies to be in the cluster, right? So how does one ascertain that those galaxies actually belong to the cluster? I mean, how do we know that they're not in the background or in the foreground? How does one do that?
So in simulation, this is in simulation, right? So you know the full 3-dimensional position of the galaxy itself. And usually how we know, usually we through friends of friends algorithm. So you look at this galaxy, you look at its neighbors, and you find out how far the neighbor is. Then you look at this galaxy's neighbors, and you build that friends of friends algorithm chain. and that's how you make a cluster, make a cluster. Or if the friends of this particular galaxies, they are really far away, then it means that those friends probably are not really friends, they are just acquaintances, they are not part of the cluster. But if they are very nearby, then they are probably part of the same galaxy. So in this particular work, since we already had information through this friends of friends algorithm, like which are the clusters and where their location are. The clusters through this friends of friends algorithm, they are extremely diffuse, and we were trying to look at the cores of the cluster. So we had specifically selected galaxies which are within twice the virial radius. We already knew the virial radius of the cluster, so we had only picked out galaxies which are within twice the virial radius to be part of the cluster. Everything else is still falling into the cluster because the infall region is quite big usually.
I had another question. So you talked about the metallicities, right? So you said that the galaxies in a given environment, they tend to have a similar sort of metallicity trends, right?
Sure, depending on their trajectory, yes, on average.
On average. So what about the incoming galaxies? So do they tend to sort of contaminate the existing environment, or does the shift happen the other way? The environment tends to.
So that is exactly the reason why we were separating this infalling galaxy, because when we look at when we just combine all the galaxies in a cluster, they can be galaxies which have been in cluster for like past 100 million years, and then you are combining them with galaxies which have been in the cluster environment for the past 1 giga-year, 2 giga-years, or throughout the lifetime of the history. And the galaxies which have just fallen into the cluster, it's going to have a very different evolutionary history compared to our galaxies which have been in the cluster for the 10 billion years, right? And that's why we were trying to separate out. This is not a full separation. We could have gone a step further, in which we could have separated galaxies which have fallen into the cluster for the past 1 billion years, or have been in the cluster for 10 billion years. But hey, there's always room to move the project forward, right? There's more you can do always. But even with this very crude definition, we found that these infalling galaxies, which are these, I wish I could stop the animation somewhere. Okay, wait. Yes, let's stop it here. Oh, come on, stop. I don't know how. Sorry. It looked like a group previously, but that's okay. So this infalling galaxies, the green crosses here, even those galaxies, they had higher chemical content than the field galaxies which are in the low density environment. And these infalling galaxies, we think because they are falling in as part of groups. So you can see here, I'll show you in a second. Okay, so you can see these greens, they are, instead of coming in more as isolated galaxies, some of them are isolated individual galaxies, but a lot of them are part of these small groups, right? And that we think that because they are part of these small groups and there are interactions happening within galaxies when they are part of this small group, that actually also boosts the average chemical content of these infalling galaxies. I hope I answered your question.
Yeah. I had one more doubt off the talk. So you said that you were interested in evolutionary biology. So how did that shift happen from bio to astro? So was there anything in particular that sort of attracted you towards astro?
Particularly astro, I think it's because in astronomy, it's not just one thing that you are studying. You're studying really large systems like galaxies, and there's everything here that you can learn and all sorts of physics that you can use. It's not like just quantum physics, which is very, very, very small scale. You can look at the quantum physics in galaxy, and there are phenomena in galaxies which are because of the quantum phenomena. But you can look at thermodynamics, you can look at fluid dynamics, you can look at spectroscopy, which is what I do. And So I think it's just that astronomy is pretty, first of all. Secondly, it's combination of all physics, but looking at the largest scale of the universe.
And one can be interested in many things, very diverse things.
Yeah.
Yeah.
Yeah, true. I'm still interested. In evolutionary biology, genetics, and lots of other things, to be honest.
Yeah, I had a doubt regarding the same slide. So
Oh, wow. Okay.
how exactly do we get to track to the past of the cluster? Like, how do we do that? How do we get the knowledge to track it back?
Yes, good point. In observations, that's absolutely not possible, right? Because in observations, you just get one snapshot. You see a galaxy at this redshift, and that's all that you're going to see, because it takes billions of years for universe to move, and we can't be waiting for that long. But that's why simulations are such a powerful tool, because they are trying to build a mock universe from. They start usually initial conditions in any of these cosmological simulation. It comes from the CMB background, and they try to add all sorts of physics like baryonic physics, hydrodynamics, everything, and try to evolve the galaxies from this really. There's a lot of assumptions. I am just trying to simplify it. There's a lot of assumptions that's inherent in building this mock universe, but they try to build this mock universe. And when they are building this mock universe, you know where the individual particles in these galaxies they were at the previous snapshot. You know the information, because that's how your model is evolving. So within these simulations, this is the position of this galaxy, and at a previous snapshot, this was the position of this was the position of most of the gas particles in the galaxy, and that probably is the position of the galaxy in the that probably is the galaxy that made this one. And you do that for all the snapshots that exist in your simulation, and you build this evolutionary track, or we call them merger tracks, essentially. Like 3 galaxies here, they combine together to form one, and then maybe one more galaxy came at redshift of 2. Okay, you add that another one, and then you have another. This galaxy just evolving without any other mergers, and you build, and that's it. It's the simulations, basically. In simulations, everything about that's happening with your particles.
Yeah, thank you very much, Dee. Does anyone from online audience have any question? They can unmute and ask. Okay, so if not, then we can conclude this session. Thank you very much, Dee, for one. Okay, yeah. Yes, Kushi, you can type your question, or if you can unmute, then you can unmute also. So, till Kushi is typing her question, if anyone has any question or any comment, Abdul, you can unmute.
Yes, I wanted to ask, like, why do we study the reionization of universe? Like, what instigated scientists to study it? Like, why do we study it? What benefits do we get from studying it?
Okay, benefits, that's a very big question, I would say. If it's the knowledge for the knowledge sake, is that not enough benefit? I don't know.
Like, it should help us, like, does it help us to define some phenomena which happen in universe? Or like, I don't get, like, why do we study the epoch of reionization of the universe? Like,
so it's one of the really major transition that happened early on in the universe, right? And it tells you how the early universe really evolved, what were the first galaxies. Because if you know how the reionization evolved, then you know what were the key properties of those first galaxies that were responsible for reionization. And in astronomy, what we are trying to understand is how our universe essentially evolved. And this epoch of reionization is one of the key transition that happened in our universe, right? Because most of the universe before it was neutral. And after the reionization, most of the universe is ionized. There are pockets of neutral hydrogen gas, but most of it is associated with galaxies. There are some like hanging around, but most of it is associated with galaxy. So there is this epoch of reionization, which is about 1 billion years, so only in time we think. And during this 1 billion years, when you started from just the neutral hydrogen, you ended up with this completely reionized universe, which is extremely, extremely rapid transition. That's why I think epoch of reionization, in my opinion, is really popular right now. There's a lot of surveys, and I think Bharat will talk about a lot about epoch of reionization as well. He's talking, I don't know, in the afternoon session. Why we study reionization?
Actually,
I don't-
I read a paper in recent, the writer was saying that our main aim in astronomy is to study like how the begin of universe, like how the origination of universe happened. And while we're studying reionization, we are able to define how the origination, how we origin. So does it is it something like, by studying reionization, are we able to study the origination of universe, like how the universe originated?
So, okay. I think by how the universe originated, I would say you can see how galaxies formed. The universe originated originated is a bad word to use, but it came into existence. I don't know, around Big Bang. But I think epoch of reionization is something about galaxies, how you formed galaxies and the stars from just the neutral hydrogen. When did they start to first appear, right?
Okay.
That's because that's that's what drove the epoch of reionization. That's what started the reionization process.
Thank you.
Sure. I can read Krishi's question.
Yeah, I'll probably read it out for the offline audience also. So Kushi is asking, what are the languages we need to know for building a strong simulation? Like, how do we build something that's so complex as it has so many factors to be considered?
Yeah, good question, Kushi. I think Bagla sir can answer that question very well. And I think most simulations, they are written in C or C++. I don't know. So do you have any answers? Because I've only used simulations. I have not really built the simulations myself.
Well, basically, you first have to write down a detailed mathematical model. In case of cosmological simulations, gravitation is the main driving force. So you need to write down equations for dynamics of dark matter, self-gravitating dark matter. And then you have to embellish it, because there is normal matter as well, which has pressure, temperature, there is radiation. And then, of course, when stars form, there is enrichment.
Yeah.
And when you have enrichment of matter, the properties in terms of how it can radiate, what it can radiate, how it cools, etc. change. So there are a lot of segments, but for each of these, you need to have a mathematical model. And then it essentially comes down to translating that mathematical model, that bunch of equations, into a computer program. So it is hard in the sense that there are many different physical processes that you need to account for. And when you are combining a whole lot of them, you also need to be able to test each segment and make sure that that is working perfectly, and it also works correctly when you work with the combination. But think of it essentially as a bunch of equations which need to be solved on a computer.
Yeah.
And because you are representing the universe, a large volume of the universe, and you will need to solve equations either for each particle or at each location in space. So you will actually be solving a very large number of equations, maybe billions. But once you teach a computer how to solve these equations, you are done.
Yeah, but most of the simulations, because it's like, as you said, it's billions of computation step at every time step required. So they have to be really, really efficient codes. So most codes are written in C or C++, my guess. That would be my guess. In terms of language.
So there are the various generations of Fortran, various generations. There is C, C++. These are more efficient because even though it is easier to write in something like Python, and there are libraries available, there have been many studies which show that in terms of efficiency, C and Fortran are about a factor of 3 to 4 more efficient as compared to Python. Yeah. So nowadays, of course, they present these results in terms of the CO2 load, how much global warming it will cause. But this is effectively what happens. Yeah.
Yeah, okay. So there are a few more questions, but I just want to first thank Anshudi because the meeting is set to end at 1. So it might end in the midway. So I'll just first thank the speakers and then we can go back to the questions. So Anshudi, thank you very much for a wonderful talk and for interacting with us. And we look forward to have this interaction more with you. There is one offline question that is waiting. So we'll first take the offline question.
Sure. Thank you.
Yeah, so this is again regarding the simulation. I just wanted to ask what method did you use for simulation? I mean, is it simple Euler method or leapfrog or something else? And did you have to take relativistic corrections into account?
Okay. This is a question for somebody who actually built the simulation, which is definitely not me.
No, the illustrious simulation does not have any relativistic component. And so there are a whole bunch of different types of steps. Euler's is not the thing which works at this level. You need something far more accurate. But at the same time, you need you cannot use methods which are so sophisticated that the number of variables per particle or per volume element increases indefinitely. So there are intermediate things which are used, and once you have fluid elements, you actually need to use different types of methods for solving the equations. Yeah, I mean, I can discuss that in detail in person. This is not the time for that yet.
Sorry.
Sorry
for jumping in.
There's one more question from Sonit. So Sonit, maybe you can unmute and ask.
Yeah, I wanted to ask, like, while writing a simulation, we define some specific variables or specific aspects that will function inside that simulation. So how can we be sure that in the actual scenario of the universe that only those specific factors will affect that specific scenario? It might be possible that there are things that we do not know about and that haven't been programmed inside the simulation.
Yeah, absolutely. That's one of the questions about simulations always. And there are so many assumptions because we do not have, even in cosmological simulations, we don't have infinite resolution. So for example, in illustrious TNG, the simulation that I used, each particle has a mass of 10 to the power 6. So you cannot resolve individual stars. You are resolving a stellar particle. So you have to make assumptions about what are the properties of stars within them, similar about the gas, and how those gas is going to affect. So there's a lot of assumptions that go into the simulation. But what most simulations do is, and that's why we can somewhat trust them, that they try to reproduce some of the observable quantities. So for example, one of the key quantity that they try to reproduce is stellar mass function. So which is basically the number of galaxies at every stellar mass bin. In observations, we know like this is the stellar mass function. Like most of the universe has low mass galaxies. There is a bunch of high mass galaxies, but their number is quite different, quite low. And there's a very particular shape of the stellar mass function that happens because of the interaction between different processes that govern galaxy evolution, different feedback processes like supernova or region. And what the cosmological simulations they try to do is they try to reproduce it as fast as they can. Again, there's a lot of parameters that go into the simulation that have to be fine-tuned to reproduce this parameter, and all of those parameters, they are degenerate. So you can still not completely trust them, and therefore there has to be this iterative loop between observations and simulations. Okay, simulations, they can reproduce stellar mass function, but let's see if they can reproduce the sizes of the galaxy. Let's see if they can reproduce the thickness of the galactic disk. Some might do better than the others. If this model, the simulation developed using this particular parameter for galaxy evolution is not producing the sizes of the galactic disk accurately, then that tells us that, okay, stellar mass function is fine, but there is something inherent in our assumption here that is not reproducing the sizes of the galactic disk properly. So we need to further fine tune the parameter. And so it's a process, but you can't trust it completely. I would never say that simulations are correct, the ones we have right now.
I guess that answers Sun's question. So does anyone else have questions from the audience? Okay. If not, then we can end this session. Thank you very much, Anshu, for being with us here today and for a wonderful talk. So I guess I will end this meeting now because this session is over, and for the next session, the symposium, it will start at 4:30. So I'll request all the participants to start joining around 4:25 or 4:20. So we'll start sharp at 4:30. So do not get late in joining, otherwise you will miss the starting portion of the talk. And with that, I will end this session. Thank you very much. Thank you to all the audience for joining, and thank you, Anshu, to you too.
Yeah, thanks. It was great chatting with everybody.
Yeah, thank you.
Bye.
Thank you.
Okay, so I will end this meeting now.